Have you ever wondered how secure your digital communications truly are? In the age of digital dominance, securing our sensitive information has become a paramount concern. From personal messages to financial transactions, we rely on encryption methods to safeguard our digital communications. The most common encryption protocols today hinge on the complexity of mathematical problems. The idea is simple. Make the problem so tough that even the most powerful computers would take an unfathomably long time to crack them. But here's the catch. These classical encryption methods are not invincible. As computational power continues to surge at an exponential rate, the time needed to crack these codes is shrinking. What's more, the advent of quantum computers threatens to shatter the very foundations of these encryption protocols. Quantum computers, with their ability to process vast amounts of data simultaneously, could potentially solve these complex mathematical problems in a fraction of the time that even the most powerful classical computers would require. In this precarious landscape of digital security, a new hope emerges from the realm of quantum physics. Quantum cryptography, a revolutionary approach to secure communication, promises to redefine our understanding of encryption. Instead of relying on the complexity of mathematical problems, quantum cryptography harnesses the peculiar properties of quantum particles to create a secure communication channel. Imagine a security system so robust that any attempt to eavesdrop or intercept the message would immediately alert the communicating parties. A system where the very act of observing the quantum information alters its state, making it impossible for an intruder to go unnoticed. This isn't a distant dream or a speculative concept. It's the reality of quantum cryptography. Quantum cryptography stands at the intersection of physics, information theory, and mathematics. It's a fascinating field that leverages the principles of quantum mechanics to ensure the confidentiality and integrity of our digital communications. As we delve deeper into the world of quantum cryptography in this video series, prepare to have your understanding of digital security redefined. As we delve into the world of quantum cryptography, prepare to have your understanding of digital security redefined. At the heart of quantum cryptography lies quantum key distribution. Quantum key distribution, or QKD for short, is a unique method of creating and sharing secret cryptographic keys. But what sets it apart? It's the intriguing world of quantum mechanics. QKD uses two distinctive properties of quantum particles, superposition and entanglement. Let's start with superposition. Imagine a quantum particle that can exist in multiple states at once, like a coin spinning in the air, both heads and tails at the same time. Now, when we try to observe this spinning coin, or in our case the quantum particle, it collapses into one state. It's either heads or tails, but never both. This is the essence of superposition, and QKD uses this property to encode and transmit information. Now, if an eavesdropper tries to intercept this information mid-transmission, they cause the quantum state to collapse, changing the information and alerting the communicating parties. This is where we encounter the no-cloning theorem, a rule saying it's impossible to create an exact copy of an arbitrary unknown quantum state. In simpler terms, you can't copy what you can't fully know, making eavesdropping futile. Then comes entanglement, another fascinating quantum property. Imagine two quantum particles so interconnected that they mirror each other's state instantly, regardless of the distance between them. Now, if an eavesdropper tries to tamper with one particle, the other particle reflects this change, again alerting the communicating parties. These properties of superposition and entanglement enable QKD to generate and distribute cryptographic keys securely. Any attempt to eavesdrop or intercept is not only futile but instantly noticeable. This ensures the integrity of the communication and keeps the shared key a secret. Quantum key distribution, therefore, promises a level of security that classical encryption methods can't compete with. This is the power and potential of quantum key distribution, an unbreakable shield in the realm of secure communication, ready to redefine the future of cryptography. Two key principles underpin quantum key distribution: entanglement and superposition. Let's first dive into entanglement. Picture twin particles born together and forever linked, no matter the distance between them. This is quantum entanglement. Each particle of an entangled pair is inextricably bound to the other. Whenever one particle is measured, the state of its twin is instantaneously determined, even if they are separated by galaxies. This fascinating phenomenon is pivotal to quantum cryptography. It means that if a nefarious actor tries to peek at the quantum key by measuring one of the entangled particles, they inevitably affect the other particle. This disturbance is a dead giveaway, raising an immediate red flag about the attempted intrusion. Now let's turn to superposition. This principle is a bit like Schrödinger's cat, the famous thought experiment. Just as the cat is both alive and dead until observed, quantum particles can exist in multiple states at once. They're not just here or there, on or off. They're here and there, on and off, all at the same time. This is superposition. In quantum cryptography, information is encoded in these superposed states, creating a cryptographic key that is virtually impossible to crack. The moment an eavesdropper attempts to intercept and read the key, they collapse the superposition, altering the quantum state and alerting the legitimate users to the breach. When entanglement and superposition work in tandem, they provide a robust security layer for quantum key distribution. The entangled particles ensure that any interference is immediately detectable, while superposition creates a key that is secure until observed. Together, these principles make it impossible for any intruder to access the quantum key without leaving a trace of their interference. So, the next time you think about the future of secure communication, remember these two quantum principles. They are not just abstract concepts from the world of quantum mechanics, they are the bedrock of quantum cryptography, shaping the future of secure communication. Through entanglement and superposition, quantum cryptography achieves unbreakable security. Heisenberg's uncertainty principle adds another layer of complexity to quantum cryptography. Now, let's take a moment to delve into this fascinating principle. Named after the German physicist Werner Heisenberg, this principle asserts that it's impossible to precisely measure certain pairs of properties, like position and momentum, at the same time. The more accurately one property is measured, the less accurately the other can be determined. Now imagine you're an eavesdropper trying to intercept a quantum communication. Here's where the uncertainty principle comes in. If you attempt to measure the quantum information, you'll unavoidably introduce some degree of disturbance. This disturbance, in turn, becomes a telltale sign of your meddling, alerting the communicating parties. In essence, the uncertainty principle ensures that any attempt to spy on a quantum communication is fraught with, well, uncertainty. Heisenberg's uncertainty principle therefore makes quantum cryptography a formidable tool against eavesdropping. Quantum cryptography not only ensures secure communication, but also sparks discussions about the future of cryptography in a post-quantum era. As we stand on the brink of a quantum revolution, we must also consider how these advancements could potentially disrupt our existing security protocols. Traditional cryptographic methods, which hinge on the challenge of solving complex mathematical problems, could become vulnerable in the face of rapidly advancing quantum computers. These quantum machines, with their superior processing power, could theoretically break through these cryptographic barriers with relative ease. But fear not, for the world of cryptography is not standing idle. In anticipation of this quantum shift, researchers are exploring what is known as post-quantum cryptography. This involves the development of quantum-resistant algorithms designed to withstand the computational prowess of quantum computers. These algorithms aim to ensure that our digital secrets stay well protected, even in a world dominated by quantum computing. Post-quantum cryptography represents a proactive response to the evolving landscape of quantum computing threats. Quantum cryptography has transitioned from theoretical concepts to real-world implementations. The realm of quantum cryptography is no longer confined to scientific papers and high-tech research labs. It's a reality now, making strides in the commercial world with quantum key distribution systems. Take the example of ID Quantique, a Swiss-based company that pioneered commercial QKD. Their systems are operational in everyday scenarios, proving the feasibility and practicality of quantum secure communication. They are demonstrating how quantum cryptography can be more than just a theoretical marvel, but also a practical solution to real-world problems. Then there's China's Quantum Experiments at Space Scale, or QUES for short. This is a research project that successfully demonstrated the transmission of entangled photons between an orbiting satellite and ground stations on Earth. This is a giant leap forward, proving that quantum communication can be achieved over long distances, even in the face of environmental challenges. But where do these systems find their applications? The answer is in sectors where data integrity and confidentiality are of utmost importance. The financial sector, for instance, deals with sensitive data that needs top-notch security. With quantum cryptography, banks can ensure that their communication channels are impervious to eavesdropping, providing an additional layer of security to their operations. Government communications too stand to benefit from quantum cryptography. In an era where espionage and cyber warfare are real threats, having a communication system that can detect any form of intrusion can be a game changer. Lastly, let's consider critical infrastructure. Power grids, transportation systems, and water supplies are just a few examples of areas where secure communication can prevent catastrophic outcomes. Quantum cryptography can play a pivotal role in safeguarding these vital services. Quantum cryptography, therefore, is not a distant future concept, but a present reality, redefining the landscape of secure communication. It's not just about creating unbreakable codes, it's about ensuring the integrity and confidentiality of information in a world where data is as valuable as gold.